A counter is a digital circuit whose value can keep incrementing on applying a certain input. The counter which we'll design today is pretty similar to the register, but it has one extra input, the count n signal. On asserting count n, the counter should keep counting up.
Let's code one with behavioral modeling now. First, some quality of life changes. I'll add a parameter data width to the register so that later on I can instantiate multiple registers of different data widths. I'll set the default data width of the mux as 2 because 2x1 mux seems to be the most common in the design. Now I'll copy the register code to the counter and add another input. When this count n input is set, I'll just increment the internal data count. I'll reuse the same register TB only. It should be compatible after I add the additional count n input to it. I'm adding the counter modules to the includes file here. I'll quickly replace register with counter. Now I'll add the count n signal and set it to 0. I should see the exact same behavior as the register. Here's my counter module with all its signals. AD is written and read, 67 is written and read, just like register's waveform dump. Now if I set count n as 1, I should see it incrementing. And here we go. I wrote AD but I'm reading AE. 23 became 24, 16 became 17 and so on. Now I'll stop all the register read writes and let it freely count up. And it's counting all the way up. I'll quickly set it to decimal. We can see that once it reaches 255, it rolls back to 0 and just keeps going. That's what a counter does.
Now let's see how it would work. This is a 1-bit counter made with a JK flip-flop. When both J and K are 1, the flip-flop keeps toggling, which is basically up counting in binary. This circuit over here is a 2-bit counter. The second flip-flop only toggles when the output of the first is 1. So when the first flip-flop counts as 0, 1, 0, 1, the output of the second will be 0, 0, and then since it is 1, it will toggle. So 1, 1. It will be 1 again after one clock cycle, at which point it will toggle again. Now using this, we can create an n-bit like a counter like so. These muxes can either pass count n or data to the JK flip-flop, depending upon write enable signal. The count n signal comes from the previous stage of the circuit by ANDing the previous output and the previous count n signal, similar to the 2-bit case. We should also generate the count n for the next stage of the circuit using this AND gate. And finally, we should add support for bidirectional data lines just like the register circuit using this tri-state gate and this latch.
I'll copy the behavioral circuit and remove all its statements. Here, I'm adding all the wires I'll be using in each instance. The counter can generate a carry, but I don't think I will need it for now, so I'll just let it be here. The count n for the first stage comes from the input count n signal, and the MSB is the carry. I can use this generate block here to replicate the circuit inside it however many times I want. Data width amount of times should be good, 1 for each bit of the counter. Let me start by connecting the muxes. Curly brackets are used to concatenate bits into a bit array, MSB first. I already named all my wires according to what port of the JK flip-flop they would connect to. Now to add the tri-state gate and the latch to give it bidirectional input-output. And finally, I'll add an AND gate to generate count n for the next stage. Let's simulate it and see. Notice that instead of data int signal, I have Q, which is the output of the JK flip-flop. This will be a common theme throughout the series. Whenever I switch from behavioral to structural, any red signal would ultimately be the output of a flip-flop. It's counting up even past FF. So yeah, it's a counter. Now let's see if it can also become a register. I'll add those register writes and reads once again and set count n as 0. And yeah, I'm able to write and read this random data into it properly. One last test. I'll set count n as 1 again. The data read is 1 more than the value written, just like the behavioral model. So this works. Today we saw how to design an up counter with JK flip-flop. I'll use it as the program counter register for the basic CPU in the future. Thanks for watching.